Hi there, this is your favorite non-Indian math channel, and I have a limit problem that is gonna make me sweat a lot. So, well, this part is ln of something over something, so I can write it like differences. So I can say this is actually, so why wouldn't I make my problem harder? Okay, I can say this is actually ln of, let's make a new variable, y minus cosine x. And I'm imagining like this is antiderivative of something, and I evaluated this integral at b and a. So imagine if you solved an integral and got this, you would go back to here. But instead, now we went from here to here. Okay? Usually we do other ways. And so I have it from 0 to pi. So this thing is actually an integral too, from a to b. So if I differentiate this thing, I'm going to get 1 over y minus cosine x. So let's write it dy over, and I'm saying dy because y is the variable. Y minus cosine x dx. Okay, or maybe let's write this dy here. Okay, so, well, also I forgot to mention a and b are both bigger than 1. Okay, ab is bigger than 1. Yeah, and I'm gonna use this info here. If you look at here, we have y minus cosine x, so y is changing from a to b, and so they're both bigger than 1, and cosine x is at most 1, so this thing is always positive. So this thing is just continuous. Okay, and since it's continuous, and let's go a bit up, so this is an integration area that x is changing from 0 to pi. Let's say this is horrible line from 0 to pi, and this thing is x is changing from 0 to pi, y is changing from a to b. I don't know which one is bigger, but this is gonna look like this. Okay, I'm integrating on this area, and Fubini's theorem says me that you can just change them. Okay, it allows me, and since all of them are just numbers, just constants, so I can directly change them. So it's from a to b, from 0 to pi, and my the change of integrals will also change. So I have y minus cosine x, order of integrals will change. Y minus cosine x dx dy. So let's write dx here, dy. Okay, cool. So now, can I do this integral? Yeah, because I previously made a video about 1 over 2 plus cosine x integral, and we can do exactly the same method. So here y is like a constant, okay? And there I told you that it's, so here I'm gonna say this integral is I. Actually, I'm gonna say this integral is I. I don't want to deal with bounds. I'm going to say this indefinite integral, dx over y minus cosine x. Okay, and then I'm going to remember my bounds were from 0 to pi. Okay, and I'm going to just put it. Okay, so this is like I evaluated at b and a. Okay, I don't need to write it. I will remember it. I promise. So I have this thing. I want to find this integral, and I told you that we have a substitution, tangent x over 2 is equal to u. This is really important. I'm not gonna again just throw the triangle and do all of this stuff. This video is already too long. This is a hella integral. And so what we find is that dx is equal to 2 over u squared plus 1 du, and cosine x is u squared, 1 minus u squared over 1 plus u squared. Okay, so if I do y minus cosine x, so I have y minus this thing, so it's going to be y. So I have yu squared minus 1 and plus 1 more u squared, so it's going to be y minus 1 plus, so it's going to be y plus 1 times u squared over 1 plus u squared. So for this I integral, I have, so I'm putting dx, I have 2 over u squared plus 1, and I'm dividing this thing. Well, technically it's not dividing. The dx is normally supposed to be here. So at the denominator I have u squared plus 1. Also here u squared plus 1. So they're going to cancel. And I'm going to be left with 2. I can take this 2 before. It's going to be 1 over y minus 1 plus y plus 1 times u squared. And did I say du? No, this is du. Okay, well, yeah, I didn't say it's gonna be easy. So let's see what we can do here. This is almost like actually 1 over 1 plus x squared, because if I know that this is gonna have the integral arctangent. Okay, so maybe I can make it look like that, but I have a constant here, so I can say this is just 2. I can divide this thing by y minus 1, and it's going to be du over 1 plus y plus 1 over y minus 1 u squared. Okay, cool. I'm one step closer. And now I want to make this thing v squared. Okay, so I want to make it look like literally. So I don't know what the constants are going to be, but I want this thing to be equal to dv over 1 plus v squared. How can I do that? So I want to get rid of this constant. Okay, this is constant because y is constant when we're integrating with respect to u. So I can say u is equal to, so I'm gonna pick something that when I square this thing, it's gonna be equal to this thing, but reciprocal to that. So I can pick y minus 1 over y plus 1, and just if I take square root of this and say v, this v is outside of this square root. Okay, if I square this thing and multiply with that, they're just going to cancel and it's going to give me this thing. Okay, so du is going to be equal to just this thing, y minus 1 over y plus 1 times dv. Okay, cool. So I found du, so I also had 2 over y minus 1. And here, if you notice, I'm going to multiply this thing and also this thing. And I have y minus 1 square root of y minus 1. So they're going to make a square root of y minus 1 at the denominator. So I'm going to have 2 over square root of y minus 1 times square root of y plus 1. So it's going to be y squared minus 1. Okay, and I know that this is just arctangent of v. Arctangent of, well, I don't want to do one more step, so v is just this thing times, I'm just going to flip this thing, throw it to the other side. It's going to be u times, I can also write u is tangent x over 2. We gained a lot of steps, cool. Tangent x over 2 times this thing. So it's going to be y plus 1 over y minus 1. Okay. Plus c. Yeah, plus c is for the careful viewers. Yeah. So this is my integral, that is I. But remember, yeah, I remembered it. So I want to evaluate this thing from 0 to pi. Let's call this thing, this whole thing, I1 when I evaluate it from 0 to pi. Okay? So I1 is going to be when I evaluate this thing at, so I'm not going to write this whole thing. Okay? Imagine this is a. So I have a from pi to 0. Okay, so if I put pi, okay, so here this thing is just a constant. Okay, let's say this is b. So I have arctangent of tangent x over 2. Of course, this is not equal to just x over 2, but this thing is quite much linear. It's not linear literally, but so when I put x is equal to pi, it's gonna be tangent of pi over 2, which is gonna give me infinity. And even if I multiply it by b, it's gonna be the same infinity. And if I take arctangent of infinity, it's gonna give me pi over 2. Okay? So it's gonna be, I'm taking this constant. So I have, I said pi over 2 And if I put 0, the bound 0, it's going to be tangent of 0, which is just 0. Arctangent of 0 is also 0. So I get 0. So I can just cancel these 2's, and this integral is going to be equal to pi over y squared minus 1. Okay, cool. Well, it's pretty simple for such problem. So, well, of course, this is almost at most half of our answer. So what did we find? I found that my integral is actually something a bit simpler from a to b. It's pi. I can just take this pi in front of the integral. 1 over y squared minus 1. And I have dy. Okay, let's write it here. Okay, cool. Well, you can either know this integral by heart. I don't. So I have y squared minus 1. Which substitution I should make? It's not sine or cosine. We can either make cosine hyperbolic, because 1 plus sine hyperbolic is cosine hyperbolic, or I can make secant. Here the logic is that if I say secant, I know that secant squared minus 1 is just tangent squared. Or I could pick, okay, we can pick cosine hyperbolic. I think saying making the substitution secant is more popular, so we can do the other way. So cosine hyperbolic squared minus 1 is going to be sine hyperbolic squared u. This is the logic why I can make the substitution secant or cosine. Okay, cosine hyperbolic. So let's say y. So this is going to be my answer. Okay, first of all, this I is what I want. Okay, let's say this is I3. I used so many. Okay, so I3 is my eventual goal. Okay, so I can instead evaluate this integral just normally. Okay, I'm gonna also leave the pi outside. In the end, I'm gonna try to remember I need to multiply it by pi. So I want to evaluate this 1 over y squared minus 1 integral. So I said I'm gonna use square root of so I'm going to use cosine. So I have y is equal to cosine hyperbolic. Let's say u. Let's not use u. Did I use? Yeah, I'm going to use u. It's not the u like in the previous example. Okay, it's just different u. I don't want to use all of these letters. So if I differentiate it, dy is cosine, derivative of cosine is just sine. You should be careful, it's not minus sine. Sine hyperbolic u du. And as I said, cosine hyperbolic minus 1 is going to be sine hyperbolic. So from the denominator, I'm going to get sine hyperbolic. And also at the denominator, I have sine hyperbolic. So this integral is just going to be 1 du. What is this thing? Sorry, I think I wrote dy here. Yeah, it's dy. So this is going to be du. Okay, so it's going to be u, which is just cosine. So this is u, but plus c. I don't know what is u. I know what is cosine hyperbolic of that. So I actually want the inverse of cosine hyperbolic, because u is technically arc cosine hyperbolic u. But it doesn't really make sense. I don't know what is that. Okay, sorry, this is why. So how can I find inverse of cosine hyperbolic? We should write its definition. Cosine hyperbolic is equal to e to the u plus e to the minus u over 2. So if I just multiply it by e to the u and divide, so it's going to be e to the 2u plus 1 over 2e to the u. Now if I just multiply all sides by 2 times e to the u and send this on this side, I'm gonna get, let's write it here, it's gonna be e to the 2u and minus 2y e to the u plus 1 is equal to 0. I'm trying to solve this thing for u so that I'm gonna get what is u in terms of y. Well, this is almost like a quadratic equation, I can say e to the u is equal to v. So it's going to be v squared minus 2yv plus 1. So I can just half this thing. I'm going to get v is equal to, if I half this and multiply by minus, it's going to be y plus minus square root of just this thing minus c y squared minus 1. Okay, cool. So v is just e to the u, and so if I just take log of both sides, u is equal to, let's say, ln of this thing. But here, let's write y plus minus y squared minus 1. So am I going to take positive or negative? Here, well, I can think like y squared is just greater than y squared minus 1. So even if I just look at the y minus y squared minus 1, it's going to be positive. So there's no actually problem with that. We can take positive or negative. If you look at inverse of sine hyperbolic, you are going to see that it can only be the positive one. But here it can be both. And this is actually assumed that we are taking the positive one. Okay, so let's take the upper one. Okay, so I'm saying u is equal to this thing. So what did I find is that I found u, and what was u? U was my answer. So if you look here, my answer was u plus c. And in the end, I want to evaluate this thing by that. Okay, so I found that u is just ln of y plus y squared minus 1 plus c. And so I want to evaluate this integral from pi and between a and b. So my I3 is going to be this integral. I'm going to multiply it by pi, and I'm going to put my bounds. And I can directly put bounds. So I have ln of, if I put b, it's going to be b plus b squared minus 1. And if I put a, it's going to be minus of that. So I can just write it at the denominator. A plus a squared minus 1. And this is actually my answer. Yeah, it was a long adventure.